Let's continue from our previous classes, and we have seen that the shape functions play the major role, because without shape functions we cannot do any finite element calculations. We need the shape functions for interpolation and also for forming the B matrix, and then for doing all the calculations like n transpose B dV or B transpose B dV and so on. And let us see how we can define or develop the shape functions by the classical methods. By classical I mean the methods that were originally developed, the generalized coordinate method, and later we have this Lagrange methods, and then after this we have more recent ones like isoparametric and so on. And before we go into more advanced elements, let's look at the classical methods for developing the shape functions. See, these shape functions, they are basically interpolation functions, and because they depend on the shape of the element, they are called as shape functions in the finite element context. And the shape functions, they express the variation of the nodal variables over the element. Then they also help us in getting our B matrix and so on. And theoretically, these the continuum can have infinite number of nodes and elements, but it is not possible to include infinite numbers. We can only include a finite number of nodes and finite number of elements. And in fact, the term finite element was coined by Professor Clough in 1960. That is just about the time when the digital computers were coming in, and the power of the computers was also gradually increasing. In fact, in those days it used to increase exponentially, but now it has more or less stabilized. Okay? And Professor Clough in 1960, he coined the word finite element, because actually we can have infinite number of elements and infinite number of degrees of freedom, but we are considering only certain number of finite elements. From that this word finite element was coined, and our requirement for monotonic convergence is, as we include more and more number of elements by decreasing the size of the elements, we should or finer mesh, our numerical solution should be tending towards the exact result, and that is called as the monotonic convergence. And so let us see what exactly we mean by comparison between our numerical result and then our theoretical result. Okay. Let us see it in the context of simple simply supported beam. Let us say that we have 2 elements and 3 nodes, and at the 2 ends it's a simply supported beam, so the displacement is 0. And let us say that whatever numerical method that we have, it is exact. So at the center point also our numerical result is exactly matching with the exact result. But then what about in between? In between these 2 nodes, there is a large variation between the theoretical solution that is given by this red line and this dotted line. So this is the numerical error that we have, and so actually we see that at most in most locations our predicted displacement is lesser than the theoretical one. So that means that our stiffness is overestimated. Only when we have a higher stiffness we get lower displacement. So we are inadvertently over predicting the stiffness, and that over prediction can be reduced by introducing more number of nodes in the mesh. Let us see the same thing for larger number of nodes and elements. In this case we have 4 elements and 5 nodes, and once again let us assume that at all these nodes we are exact, our solution is exactly matching, let us say, and then that is only an assumption that may or may not be true, and in between we see that there is still some deviation between the theoretical result and then the finite element result, but this difference is smaller compared to what we had before. Here the difference is large, whereas here it is smaller. Then let us make it more finer. Let us consider 6 elements, 1, 2, 3, 4, 5, 6, and in this case the elements around the load are made smaller, and then here we see that we are even more closer to the theoretical result, and so as we are including more number of nodes and elements in the mesh, we can come closer to the theoretical result, and that is what we mean by monotonic convergence. And it is not an automatic process, so we have to take some precautions so that as we include more number of nodes in the mesh, our solution is tending towards the exact result. Okay. So the development of shape functions is a very important step in all the finite element analysis, and we should be very systematic so that our results are also as accurate as possible, and our aim is to satisfy the requirements for the monotonic convergence, and as the mesh is made more and more finer, the solution should approach the exact solution, and the criteria are very simple. The shape function should not permit straining of an element to occur when the nodal displacements are caused by rigid body displacements. That is what we had seen earlier. So, if this pen, whether it is here or here, there are no strains or stresses within the element within the pen, because it has undergone only rigid body displacement, like all the points on the pen have undergone the same displacement. So, that means that there is no relative displacement between 2 points on the pen, or no strains, and if there are no strains, there are no stresses, and that is what we mean by the first condition, that if you subject a body to rigid body displacement, the shape function should be such that they should not predict any strain. And then the second condition is, if the nodal displacements correspond to a constant strain condition, we should be able to predict that same constant strain. Okay, that we will see with an example. And the shape functions should be such that the strains at the interface between elements are finite, and the continuity of displacements need to be ensured. Okay, because we will come across the interface between different elements, and at those points also we need some continuity of displacements and then the continuity of strains, and there should not be any singularity in the shape functions. The shape function should be well defined at all the points within the elements. What we mean by continuity is like this. Let us consider mesh consisting of 8 node quadrilateral elements, and let us look at 2 elements A and B, and these 3 highlighted nodes are common for both element A and element B. And if you look at the displacement at these points, whether you are looking from element A or whether you are looking from element B, we should get the same displacements. And if you get the same displacements, that means that we are maintaining the continuity of the displacements. Okay? And the displacement at these 3 points calculated from A will include the displacements at all these 8 points, whereas from B they will include all these 8 nodes. Okay? And the strain continuity at the interface may not be satisfied or may be satisfied only approximately, because the strain is not our field variable, it is only a derivative quantity, and the continuity of strain can be simulated by making the mesh as fine as possible. So, if you have a very coarse mesh, we may not be able to get the strain continuity between the elements, but if as the mesh is made more and more finer, we will get the strain continuity. So, here we have taken both elements A and B of the same type, both are 8-node quadrilaterals, and now let us consider an interface between a 4-node quadrilateral and an 8-node quadrilateral. Say a 4-node element it has only 4 nodes. So, along each line we have only a linear function. Okay, so it's we call it as a linear element, whereas an 8-node element is a quadratic element. It is along each line there are 3 nodes. Okay, and so the displacement that we predict from this side, from the 4-node element, may not match with the displacements that we get from 8-node element, because one is a linear function of displacements and the other is a quadratic function of displacements. So, we will not be able to maintain the continuity, or we call it as incompatibility between the 2 elements. So, one way to overcome that is by reducing the size of the elements, so that we get a better representation, and invariably we will have to do this type of thing, like linking 4-node elements to 8-node elements and so on, especially in the transition zones. Okay. So, our generalized coordinate method, the polynomial expansion, use it to express the internal displacements in terms of the nodal values. Okay. And then the number of polynomial terms is equal to the number of nodes in the element, and then the polynomial terms are constructed from the lowest order, that is the constant term, linear, quadratic, cubic and so on, and the polynomial terms should be spatially isotropic, so that the results are independent of the coordinate system. Whether you take a coordinate system like this x and y, or x and y, x vertical and y horizontal, or y going down instead of going up, whatever may be the coordinate system, the result should be the same. Okay, numerical value of the result. To help us in satisfying the spatial isotropy, we can take the help of this Pascal triangle that gives you all the polynomial terms of different order: constant term, linear x and y, quadratic x square, x y and y square, and then cubic x cube, x square y, x y square, y cube and so on. Okay. And the choice of polynomial terms, so the number of terms in the polynomial should be equal to the number of nodes in the element, and as far as possible the polynomial should be complete and the symmetric. Complete in the sense should include all the lower order terms before you start including higher order terms. Okay. And the constant term is required to be able to simulate rigid body translation without straining the element. Then the linear terms are required to be able to simulate the constant strain condition. See, these three they are observed only from experience. Okay, that we will see with an example. What happens if you do not have a constant term, or if you do not have a linear term and so on. Okay. And these are some of the typical elements, and then the polynomials. So, you can have a 4-node quadrilateral like this, either a rectangular element or a distorted element like this, and the polynomial for a 4-node quadrilateral can be a0 plus a1x plus a2y plus a3xy, and this is a spatially isotropic expansion, because for every x there is a y. Okay. and our strains are epsilon xx is dou u by dou x, that is alpha 1 or a1 plus a3 plus a3 y, and epsilon yy is dou v by dou y, that is a2 plus a3 x, and gamma xy is dou v by dou x plus dou u by dou y, that is equal to a1 plus a3y plus a2 plus a3, sorry, it should be x. Okay. And for an 8 node quadrilateral, our polynomial can be like this: a0 plus a1x plus a2y, that's including the constant term and then the linear terms, then the quadratic terms x square a4y square plus a5xy plus higher order terms a6 x square y plus a7 xy square. Actually, let us look at our Pascal triangle. So, when you have a 8 node quadrilateral, we have this constant term 1, and then the linear terms x and y, and then the quadratic terms x square, xy and y square. So, these are 6 terms, and we need 2 more terms, and we can include either x cube and y cube, so that we have the spatial symmetry, or x square y and xy square. So, how we decide whether to take x cube and y cube or x square y and xy square is very simple. So, in the 8 node quadrilateral, along each line we have only 3 nodes, right, and if you have 3 data points, the maximum order of polynomial that you can fit is 2. So, we can choose these 2 terms x square y and xy square. Then we are satisfying the spatial isotropy. For every x there is a y. So, even if you interchange x and y coordinates, it does not matter, because our polynomial expansion is spatially symmetric. The 9 node quadrilateral, the polynomial is like this, and for choosing the polynomial terms for higher order elements requires the observations from the Pascal triangle. See, for 8 node quadrilateral, we have the terms up to x square y and xy square, and for the 9 node quadrilateral, we can include this term x square and y square, because in the 9 node quadrilateral also, along each line we have only 3 nodes. So, that means that maximum order of polynomial that you can fit is only 2. So, we can choose x square y square as our 9th term, and as we see, all the polynomials that we have for the quadrilaterals, they are incomplete. See, in the for the 4 node quadrilateral, we have a0 plus a1x plus a2y plus a3xy, and but we are missing x square and y square terms, and in the 8 node quadrilateral we are missing x cube and y cube. See, for the 8 node quadrilateral, we included these 2 terms x square y and xy square, but missed out on x cube and y cube, and for the 9 node quadrilateral we have included x square y square, but we did not include x cube y, xy cube, y4 and x4. Okay. So, all the quadrilateral elements, they have an incomplete polynomial. And let us look at the triangles. The 3 node triangle we have already seen. Let us look at the 6 node triangle, 10 node and 15 node and so on. See, the 6 node triangle, it need not have straight edges. We can have a curved edges like this, and our 6 node triangle, we also call it as a linear strain triangle, LST, because the strain is linear and the polynomial expansion is a0 plus a1x plus a2y plus a3x square plus a4y square plus a5xy. And so for the 10 node triangle, it's a quadratic strain because we have a cubic variation of displacements. So that means that the strain will be one order less, that is x square y square. So it is quadratic. And the 15 node triangle, it's called as a cubic strain triangle because our displacements are of the fourth order. So the strain should be of third order. And this is the expansion for a 15 node cubic strain triangle. See, if you look at the number of terms in the Pascal triangle up to any particular row, up to second row we have 3 terms, and up to third row we have 9 terms. 3 plus 3 9. 3 plus 3 is 6, not 9. Okay, and then up to fourth row we have 10. 6 plus 4 is 10, and then in the quartic terms in the fifth row we have 5 terms, 1 2 3 4 5. So 15 terms. And if you look at the number of nodes in the triangles, it is 3, 6, 10, 15, and then next one will be 21, and so on. So our number of nodes in the Pascal triangle allows us to have complete polynomial like alpha naught plus alpha 1x plus alpha 2y, or including alpha 2x square, alpha 3xy, alpha 4y square, and so on. Okay. So our triangular elements, they allow us to have a complete polynomial. And this next one is a 21 node triangle, and these triangular elements, they have a complete polynomial, and that gives us some advantage. In fact, we get more stable numerical solutions because our polynomial is complete, and because of that some spurious modes of displacements are not excited, whereas we will have problems with the quadrilaterals like 4 node quadrilaterals and so on. Okay. So in the geotechnical program Plaxis, that is one of the most popular commercial programs, they give you option of only 2 elements. One is a 6 node triangle and the other is a 15 node triangle. Both are known to perform well, and depending on the nature of problem that you have, you can either choose a 6 node triangle or a 15 node triangle. And we can look at the influence of the polynomial choice using 1D examples. Like say if you want to do any 2-dimensional examples, we have to go in for finite element analysis. We cannot do by hand, and by doing some simple calculations by hand, we can see what is the effect of different orders of polynomial. Let us consider once again a 2 node bar element. It is an axial element, so we have only one displacement u. Node 1 displacement is u1, node 2 displacement is u2, and our polynomial is alpha naught plus alpha 1x, and it is a complete polynomial of the first order because we have a constant term alpha naught and the linear term alpha 1x. So if you determine the shape function that we had already done several times, our u of x is u1 n1, where n1 is 1 minus x by l, plus u2 times n2. N2 is x by l, and our n1 and n2 are either 1 or 0, 1 at their own node and 0 at the other node, and our n1 plus n2 is exactly equal to 1, and the strain within the element epsilon is dou u by dou x, that is you will get u2 minus u1 by l, and the strain is constant within the element, and then if you subject this element to a rigid body displacement, that is u2 and u1 are the same, the strain within the element is 0. So, if you subject this element to a rigid body displacement, will predict a 0 strain, and if you apply a strain corresponding to or displacements corresponding to constant strain, your strain is constant within the element. So, that means that this polynomial that we have assumed for the 2-node bar element will satisfy our requirements for the monotonic convergence. And let us repeat the same problem, but now let us do without the linear term. Let us take two terms, u of x as alpha naught plus alpha 2 x square. So, I have neglected the linear term alpha 1 x, but included the second order term alpha 2 x square. Okay. So, if you go through the process, our n1 is 1 minus x square by L square and n2 is x square by L square, and our n1 is 1 at x is equal to 0 and 0 at x is equal to L, and similarly n2 at x is equal to 0 is 0 and at x is equal to L, that is at its own node, it is 1. Okay. And our n1 plus n2 is exactly equal to 1, and then now let us calculate the strain. Epsilon is dou u by dou x, that is dou n1 by dou x u1 plus dou n2 by dou x u2, that is 2x times u2 minus u1 by L square. So, if you subject this body to rigid body displacements, that is u2 is equal to u1, you will get a 0 strain. But then you see the strain is varying linearly within the element. So, if you subject this body to some constant strain, like let us say you set the u1 to 0 and u2 to some value, you will see that the strain is varying linearly along the element because it is a function of x. So, we are not able to represent the constant strain condition, and because it is missing the linear term, and so we can say that this element may not satisfy the does not satisfy the monotonic convergence requirement. So, if we use this element, we may not get good results, we may not get the monotonic convergence. Okay. So, now let us do one more attempt, now without the constant term. The u of x is alpha 1 x plus alpha 2 x square. Okay. And we get some functions like this, and then our n1 plus n2, we see that it is not equal to 1, and our strain within the element is dou u by dou x, is also a bit complicated function, and if you substitute u1 is equal to u2, the strain is not 0. So, that means that the element predicts strain even when we subject the body to rigid body motions. That is because we do not have the constant term. See, to be able to represent rigid body displacements without developing strains, we must include the constant term, and in this particular case we have not included the constant term. So, we fail to represent the rigid body motion without strains, and this element can also represent constant strain. So, if you substitute u1 of 0 and u2 of some value, we have this x in the equation. So, that means that your strain is going to vary linearly. So, by neglecting the constant term, we fail to represent the rigid body motion without straining, and then even the constant strain state. Whereas previously, when we included the constant term but missed out on the linear term, we were able to represent the rigid body motion without straining, but then we failed to represent the constant strain state. And here we failed in both in the rigid body and also the constant strain. So, you might be wondering why. See, we have the linear term, so we should be able to represent a constant strain condition, but then see, even the rigid body motion also is a constant strain condition, because it's like whether I have the pen here or there, the strain is 0 all over, and that is also a constant strain. Its only thing is the strain value is 0. So, even the constant strain condition that we get under rigid body motion, that is 0 strain, that is also a constant strain, and so without the constant term alpha naught, we will not be able to represent the constant strain conditions, and although you have this linear term, it does not help very much, because you do not have the constant term. So, it is very important that when we develop our shape functions, we are systematic and we include all the lower order terms. So, we extend the same thing for a 3-node bar element, and we assume a polynomial like this alpha naught plus alpha 1 x plus alpha 2 x square, and this is a complete polynomial, because you have all the terms up to x square. Okay. And you notice that the third node is at the mid length, node 1 and node 2. See, for defining a bar element, we require minimum 2 nodes, and naturally we will keep these nodes at the 2 ends, and if you want to place more number of nodes, then you can choose some interior points. In this particular case, the node 3 is placed at mid length, but it could be placed anywhere else, and our we can determine alpha naught, alpha 1 and alpha 2, and we had seen this example earlier. We see that n1 plus n2 and plus n3 is exactly equal to 1, and if you subject this element to rigid body displacements as u1 is equal to u2 is equal to u3 is u bar, our epsilon is 0. So, that means that we are able to move the body as a rigid body without developing any strains, and then if you subject the element to some displacement field corresponding to constant strains, that is u1 is 0, u2 is u and u3 is u by 2. We do predict the strain as u by L, that is constant within the element. So, by choosing the constant term and the linear term in the polynomial, we are able to represent the rigid body motion without developing strains, and then if your displacement field is corresponding to constant strain, we are able to represent that. So, this element is satisfying the monotonic convergence requirement. So, if you increase the number of elements, we will be approaching the theoretical result. Okay. So, now let us continue for higher order elements like a 6-node triangle. So, earlier we had derived the shape functions for a 3-node triangle, and if you remember, with the 3-node triangle we got the coordinate matrix, a 3 by 3 matrix, and that we can easily invert analytically, and after we invert, we have grouped all the displacement terms under u1, u2, u3, and then came out with our shape functions. Ni is alpha naught, alpha I plus a plus bi x plus ci y divided by 2 delta and so on. But here, when you have a 6-node triangle, your coordinate matrix is a 6 by 6 matrix. So, we cannot directly write out the inverse of this matrix. So, we need some other procedure, and that procedure is explained here. So, actually it is a procedure to derive shape functions for higher order elements using an automated process. So, let us say that your u is alpha 1 plus alpha 2 x plus alpha 3 y and so on, okay, and our u is this coordinate matrix C multiplied by this alpha, alphas are the generalized coordinates. So, our alpha can be determined as C inverse AE, and our U can be P, that is the polynomial series 1 x y and so on. Okay. And so, our N can be P times C inverse, okay, and P is the polynomial vector of polynomial terms 1 x square and so on, y square and so on, and the C is the inverse of this matrix. So, but only problem here is C inverse could be very difficult to obtain. Like let us say if you are doing if you are using a 21 node triangle, you need to invert 21 by 21 triangle, and if you have some 1000 elements in the mesh, you will be spending lot of time on just simply inverting these matrices, and after you invert the matrix, then you get your shape functions and then proceed with the rest of the analysis. So, let us illustrate this process for a 2 node bar element A0 plus A1x, and this is the coordinate matrix 1 0 1 L. The C inverse is 1 by L, L 0 minus 1 1, and the N is P times C inverse. P is the matrix of this polynomial terms 1 and x, and our C inverse is L 0 minus 1 1, and then the C inverse is this, and then we have this shape function, and this product will give you the shape functions, and N1 is L minus x by L, and N2 is x by L. And we can look at one more example without the constant term. Let us take x1 at 10 and x2 at 20. So, that if you have an x of 0, then it becomes difficult to find both alpha 1 and alpha 2. So, because of that the element is translated so that x1 is not 0. Okay. So, our u at x is equal to x1 is this, and u at x is equal to x2 is u2, that is this, and by solving we get our n1 as 400x minus 20x square by 20,000, and n2 is minus 100x plus 10x square by 20,000, and then if you add up n1 and n2, you do not get to 1, you get some other value. So, that means that you cannot assure the monotonic convergence with this type of element, and then getting the shape functions using the generalized coordinate method is also very tedious, because we have to go on inverting so many matrices. Sometimes these matrices are fully populated, so inverting that will take a lot of time. So, although the procedure for finding the shape functions is automated, their determination is cumbersome, and the evaluation of the integrals is also tedious. So, if you have a complicated shape like this and I ask you to integrate, we cannot do it because of irregular boundary, and because our the two coordinates, they are not normal to each other, orthogonal to each other, whereas previously we had seen x is along x axis and y is along y axis. They are perfectly orthogonal to each other. Okay. And so, if your shape is like this, then it is difficult. We cannot easily do the integrations. So, the new family of elements that are developed are the Lagrange family of elements, and these are pure rectangular elements, and the way their shape functions are developed is slightly different from what we have seen earlier with the generalized coordinate method. And let us consider a 4 node Lagrange element. So, it has 4 nodes 1, 2, 3 and 4, and then 9 node, it has 3 nodes along the x axis and then 3 nodes along the y axis, and it could have either 4 nodes along x axis and 4 nodes along y axis, and it is not necessary to have the same number of nodes along both x and y axis. Say here we have a 12 node Lagrange element that has 4 nodes along the x direction and then only 3 nodes in the y direction, and because of that, if any quantity is moving along the x direction, the y remains constant, and then similarly if you are moving along the y, x remains constant, and we can write the shape functions n of x y as product of two separate functions, one written in terms of x and the other written in terms of y. And let us say that we have m number of nodes in the x direction and then n number of nodes in the y direction, and then the shape function in the x direction is written as the ratio between two quantities. In the numerator we have, say for ith node, it is x minus x1 multiplied by x minus x2, you continue, and x minus x I minus 1 times x minus x I plus 1, then continuing up to x minus x m, where m is the number of nodes in the x direction, and in the denominator we take the x coordinate at the ith node x I minus x 1, x I minus x 2 and so on, and then we will not have the term x I minus x I in the denominator also. So, we will have x I minus x I minus 1 times x I minus x I plus 1, and then continuing up to mth node like this. And similarly, for jth node in the y direction, n j of y is y minus y 1 times y minus y 2 and so on up to y minus y n, and in the denominator we have y j minus y 1, y j minus y 2 and so on. So, we see that in the numerator we have the variables x and y, whereas in the denominator we have only constant quantities x I minus x 1 and so on, and this could be a bit confusing, but if you look at particular elements it becomes more simple. Let us consider a 4 node Lagrange element, and it has 4 nodes 1, 2, 3 and 4, and along the x direction we have the coordinates x 1 and x 2, and along y direction we have y 1 and y 2. And let us say that we are interested in writing the shape function for node 1. So, node 1 x of x and y is equal to x minus x 1, because the coordinate at node 1 is x 2 and x minus x 1 divided by x 2 minus x 1, and similarly the y coordinate at node 1 is y 2. So, we have y minus y 1 divided by y 2 minus y 1, and similarly the shape function for node 2 will be x minus x 2 divided by x 1 minus x 2, and then y minus y 1 divided by y 2 minus y 1, because the coordinate at node 2 is x 1 y 2, and at node 3 we have the coordinates x 1 and y 1. So, we have the n 3 written as x minus x 2 divided by x 1 minus x 2 multiplied by y minus y 2 divided by y 1 minus y 2, and similarly at node 4 the coordinates are x 2 and y 1. So, we have the shape function in the x direction as x minus x 1 divided by x 2 minus x1, and in the y direction it is y minus y2 divided by y1 minus y2. Okay. And directly we have written the shape functions for all the nodes in the element, and if you look at the sum total of all the shape functions n1 plus n2 plus n3 plus n4, it will be exactly equal to 1. That you can check it for yourself. And similarly, we can extend this procedure even for higher order elements. Let us look at a 9 node Lagrange element that has 3 nodes along the x direction and 3 nodes along the y direction, and we have the nodes 1, 2, 3 and 4, and then 5, 6, 7, 8 and 9, and you notice that we have first numbered the corner nodes first, because for defining a rectangle you require minimum 4 points and 4 corner points, and then 5, 6, 7, 8 they are the intermediate points along each direction, and the 9th node is at the center of the element. Okay. So, at node 1 n1 of x will be x minus x1 times x minus x2 divided by x3 minus x1 and x3 minus x2. Okay. Because the coordinate value at node 1 is x3 in x direction and y3 in y direction. So, in the y direction your shape function will be y minus y1 multiplied by y minus y2 divided by y3 minus y1, y3 minus y2 and so on. And let us look at node 9 where the coordinates are x2 and y2. So, the shape function in the x direction will be x minus x1 multiplied by x minus x3 divided by x2 minus x1 and x2 minus x3, and in the y direction we have y minus y1 and y minus y3 divided by y2 minus y1 times y2 minus y3 and so on. Okay. And the sum total of all the shape functions will be exactly equal to 1. Okay. And so, the advantage that we are gaining now is we can directly write the shape functions. We do not need to go through the inversion of a large matrix, coordinate matrix and so on. And the main advantage of these Lagrange elements is that the shape functions can be directly written without going through a complicated matrix inversion. But then there are several other disadvantages. There are too many internal nodes, like as we have seen earlier. See, all these are like for a 16 node element, these are all the internal nodes, and for the 12 node element these two are the internal nodes, and for the 9th node this is the internal node and so on. Okay. And these internal nodes, they do not help us in this inter-element continuity. We cannot satisfy the compatibility conditions along the edges of the elements, and so because of that the solution is not improved corresponding to the effort that you take. Okay. And we also use too many higher order polynomial terms which are incomplete, and the polynomial terms are complete only to a lower degree, and there could be wild fluctuation in the shape function, especially if you have too many nodes. So, your shape function will be either 0 or 1, 0 at all the other nodes and 1 at its own node, but in between we have no control, because if you have a very high order polynomial, there could be a lot of fluctuations like this, and so that could lead to numerical difficulties, because if you are operating at some other some location in between the nodes, your shape function could be very high, and that could lead to numerical problems. So here like if you look at this 9 node Lagrange element, we have seen that in the x direction for node 3 we have the shape function in the x direction is x minus x1 x minus x2 divided by x3 minus x1 x3 minus x2, where x is a variable and then the y is the variable in the n2 of y. And so for this particular node n32, that is this this node, the polynomial terms, if you expand and then take the product, will be something like this. We have an x square and then x times x1 x minus x times x2 and so on, and then similarly the y direction. So we have the polynomial terms x1 and x2, these are constants, and so we have a constant term x and y, and then xy, y square, x square, y square, x square y, xy square, and so on, while we are missing some other higher order terms like x cube and y cube. See, corresponding to x square y and xy square, we should have x cube and y cube for our complete polynomial, that we do not have, and corresponding to x square and y square, the other fourth order terms are x to the power 4, x cube y, xy cube, and y to the power 4. So these are missing in our polynomial. And so if you look at the included terms for the Lagrange element, for the 4 node Lagrange element, we have 1, that is the constant term x, y and xy, while we are missing x square and y square. Whereas for the 9 node Lagrange element, we have all these highlighted terms, while we are missing these terms x cube, y cube, and then x cube y, xy cube, x to the power 4, y to the power 4, okay, and so on. Like if you extrapolate for 16 node Lagrange element, we will have more number of terms, but then we are also having more number of missing terms. And we already know that for getting accurate finite element results, we should have a complete polynomial, and that we have seen even from the earlier methods, classical methods like the Rayleigh-Ridge and other methods. So just to summarize the comments about the classical methods or the generalized coordinate method is that even after getting the shape functions, computations are not easy, especially if you have an irregular geometry, a curved boundary or something. Integration of the quantities is not easy, and then we cannot accommodate curved geometries, and we cannot model these curved geometries with either triangular elements or rectangular elements. And because of these problems, the Lagrange elements have not become very commonplace, although the procedure is beautiful because we can directly write the shape functions and so on. And so this technique, the Lagrange elements, have not become popular, but then this technique is quite attractive for deriving shape functions for higher order elements, and that we are going to see from next lecture onwards, because we need to make some changes to make all the calculations amenable for computer operations. Like we should be able to easily program these different integrals for calculating the stiffness matrix, load vector, and so on, and that we will see from the next class onwards. And so thank you very much. We will meet in the next class.